So we have seen so far linear combinations and notion of span. The next very important notion in a vector space is that of a subspace. Okay. What is a subspace? Suppose somebody gives you a very big vector space and you are a little worried about whether you will be able to understand something so big or not. You can look at portions of it, smaller pieces of it, which are already vector spaces of their own. Okay. So if you have such subspaces, then studying vector spaces becomes really easy. Okay. So that's the idea behind looking at subspaces, smaller subsets of the vector space which are vector spaces by themselves. Okay. So that's what this definition means. A subset of V, U, okay, is called a subspace if U itself is closed under vector addition and scalar multiplication. So if U itself is like a vector space or a vector space actually, right. So U itself is a vector space over F, and then you say it is a vector subspace. Okay. So you might wonder why you study subspaces. You will see later on there are really powerful theorems that are very useful, and all of them rely on these subspaces and a lot of ideas surrounding them. Okay. So subspaces are very important to understand a vector space. Okay. So I have given here examples for subspaces. Okay. Remember, a subspace needs to be a vector space by itself. So let us look at R2 and R3 for instance, right. So in R2 and R3, which is the plane and the just the real plane and the real vector space R3, right. Lines and planes through the origin are all subspaces. Okay. So let us take a look at how that would be. Okay. So if you look at R2, which I will have to once again draw, let me draw the plane axis. I will draw the next one here. Okay. Okay. So this is R2. Any line through the origin. Okay, so let's make the origin a little bit here. Okay. So any line through origin is a subspace. Okay. So this naturally begs the question, what about lines that don't pass through the origin? Okay, so let's say you take a line like this. Okay, this is also a straight line. Okay. So a very interesting question is whether this is a subspace. Okay, so this is also a subset, right? A line in 2D plane is also a subset of the vector space. A question you can ask is this a subspace? Okay. So it turns out this is not a subspace. Okay. A very easy check for a subspace is, see, a subspace should be a vector space by itself, which means what? It should definitely have the 0 vector, right? A vector space should have the identity element. So if the subspace does not have the origin, there is no chance that it can be a subspace, right? If any subset does not have the origin in it, there is no chance that it will be a subspace. Okay, so that's one very easy way to eliminate lines that don't pass through the origin. They will not be a subspace. You can also check. You can take any line that's not passing through the origin, take 2 points on that line, and then add them together. You will get a point that's not on the line. It will be outside. Okay, so it's most easy to illustrate with a very simple example. Supposing I take this very simple example of a line, that's parallel to the y-axis, right? Okay, so if I take a point here, this would be let's say 1, 2, 3, 4, 4, comma 0, and then I take another point here. This would be maybe 6. I'm sorry, this is 4, comma 1. Okay, and this would be 6, comma 1. If I add these two, what happens? 4, comma 1 plus 6, comma 1. I get 10, comma 2. Okay, where is that? That's somewhere here. Okay, so this is 10, comma 2, and clearly this is not on the line, right? Okay, so you can clearly see the lines that don't pass through the origin will not be subspaces. Okay, same thing is true with R3. You can think of R3 as the 3-dimensional space here, and then if you have planes that go through the origin, you have subspaces, and lines that go through the origin, you have subspaces. But if a line does not go through the origin, plane does not go to the origin, or any other surface, sphere or cylinder or something else, cone, etc., they are all not subspaces. Okay, so you can quickly see why that would be not true. Okay, so that gave you a picture of visualizing how a subspace would be, and here are a couple of more definitions which I like. This is also a way in which people typically describe subspaces. Look at this definition. Okay, so you can check that this is a subspace. You can take 2 points of the form x1, x1, y1, and then you add it to, you do linear combinations, a times this, b times x2, y2, I'm sorry, it's x2, y2. You will get, you can check that this would be ax1 plus bx2, comma ax1 plus bx2, comma y1 plus y2. Right? This also belongs to the same space. It has that form. So the first x comma y, what does that mean? The first two coordinates are identical. The third coordinate can be anything else. That is a subset. That's the way I am defining my subset of F3. And that ends up being a subspace because the linear combination is closed, right? It's within that. So it becomes a subspace. You can check that. That's very interesting. So you can think of what that will be in F3, right? So if you think of the F3 three-dimensional space, what will be x comma y? If you think of the 2D plane, right, xy plane, right, x comma x is the line, 45-degree line through the origin, and then y or the z coordinate can be anything, right? So it's a plane like that. Okay, it's a vertical plane, and it cuts the xy plane at the 45-degree line. Okay, so that's how you can visualize if you like. Of course, if you have a much larger dimension vector space, it's difficult to visualize it like this, but here you can do that. Okay, so look at the next one. The next one is also very interesting. So you have this x, y, z such that x plus y plus z equals 0. Okay, again, if you take 2 points, x1, y1, z1. So let me write here. So for this one, x1, y1, z1, and x2, y2, z2. Remember, x1 plus y1 plus z1 would have been equal to 0, and x2 plus y2 plus z2 is equal to 0, right? So x1 plus y1 plus z1 equals x2 plus y2 plus z2 equals 0. I know that that's true. Okay. So then what will happen if I do ax1 plus bx2, right? So you see clearly that ax1 plus bx2 plus ay1 plus by2 plus cz1 plus zz2, this is also 0. Okay. So if you have, if you take linear combinations ax1, ay1, az1 plus ax2, bx2, by2, bz2, so that vector also belongs to the same subspace, so it becomes a subspace. So you can create subspace using these kind of linear relationships between coordinates, right? So that's also possible, something to keep in mind, so that you can get subspaces in different forms. Now, how will x, y, z such that x plus y plus z equal to 0 look on the the three-dimensional plane? It should be a plane through the origin, right? So if you think of z equals 0 on the xy plane, you have to have x plus y equals 0. So that will be the line. So y is minus x. Okay, so you will have this line minus 45-degree line, right? So that's the line that will be. And then how will you push it to larger and larger z? Think about it. So once you have x and y fixed, so you can think of that line, and then as you vary z, you will simply get for a particular z on that plane, it has to be x plus y equal to that z, right? So it will be a line which will keep changing, x plus y equal to minus z. So you will get a different sort of a line, and from there you can get a plane that will picture it for you. Okay, so think about how that would look. It's a bit of an interesting thing. So it's this various ways to do these things. It will not be vertical or anything. It will be sort of at one angle. What angle it will be, you can think of all that and imagine how the subspace would look. But it will definitely be a plane that passes through the origin. That's for sure. Okay, so think about why that's true. Okay. So in general, here's an exercise that I've given you. You can try to prove it. You can show that the span is basically the smallest subspace that contains the entire all the vectors. Okay, so if somebody gives you a set of vectors and asks you the question, what is the smallest subspace? What do you mean by smallest? How do you define size of a subspace? So subspaces, if you say smallest, it should be smallest in size in some sense, right? So it should be contained, any other subspace that contains this should contain the smallest subspace also. Okay, so this is a nice exercise to think about why should span be the smallest subspace containing the VL. Okay, so anyway, so hopefully these examples gave you some idea of what subspaces are. If you have a big vector space, subspaces are smaller subsets which have all the properties of the vector space itself, and you can use it in interesting ways. Okay, so that's subspaces for you. So let's move on to the next important idea, which is of linear dependence and independence. Okay, so in any vector space over some scalar field, one can define the notion of a linear dependency and linear independency. Okay, so all of this starts with a set of vectors. In this case, we are going to start with m vectors v1, v2 to vm in this vector space V. I will say that this is a linearly dependent set. v1 to vm is linearly dependent if there are scalars which can make a linear combination of v1 to vm and give you 0. Okay, so now I have to be careful here, because if all my scalars are chosen to be 0, right, if ai is 0, every ai is 0, then the linear combination is automatically 0. Okay, so there's nothing great about it. So of course, if given any set of vectors, I can make a linear combination which will give me 0, which is the trivial linear combination where all my scalars are 0. Now that is not the notion of linear dependence. In linear dependence, at least one of these coefficients should be non-zero. Okay, you cannot make all of them 0. At least one has to be non-zero, and still the linear combination should end up being 0. If you have a situation like that, then these vectors are supposed to be linearly dependent. Okay, so that's what I meant here in the bullet point right below that. Linearly, okay, so something is wrong here, so let me correct it. It's not linearly independent, it's linearly dependent. Okay, so that should not be there. So vectors are linearly dependent if there is a non-trivial linear combination that can result in the 0 vector. Okay, so that way we say vectors are linearly dependent. The opposite is linearly independent. So what is the opposite? There should be no non-trivial linear combination, or another way to put it is, if somebody tells you there are scalars ai such that a1 v1 plus a2 v2 plus am vm is 0, then what should be true? All the ai should be 0. Okay, so only the trivial linear combination results in the 0 vector. Okay, so this is something that's sort of important, because if there is a set of vectors and they are linearly dependent, there is something redundant about them, right? So it's almost as if one can be formed through the others, right? So if you have a linear combination with the coefficient non-zero, you can keep that term alone on one side, move everything else to the other side, right? And then you can divide and you get one vector in terms of the other vectors. Okay, so a linearly dependent set has some redundant vectors in some sense, linearly redundant sort of vectors. So maybe you can use that, and that's something useful. On the other hand, linearly independent sets, every vector adds some new information in some sense. Okay, so this is something to keep in mind when you think of linear dependence and linear independence. Okay, so here is some examples. Okay, so the examples are in R2 and R3, and you can see given two vectors, how do you find whether they are linearly dependent or not? Okay, so that's the next question. Naturally, we start with very simple examples. Before that, what about one vector? If somebody gives you one vector, how do you find out if they are linearly dependent or not? What's the meaning of saying one vector linearly dependent? But sometimes definitions, you have to pay attention to these kind of trivial corner cases to make sure everything works out. So if you have only one vector, that vector has to be the 0 vector. If it is the 0 vector, then it is sort of linearly dependent, because you can have non-trivial combinations giving you 0. But if it is a non-zero vector, then it is linearly independent. So one vector is not so interesting. But if you have two vectors, you can ask this question: are they linearly dependent? Are they linearly independent? Okay, so that's a very valid question. So here are two examples I've given here in R2. You can see very easily that without too much thinking, you can quickly say these are linearly dependent, these are linearly independent. Okay, it's not too difficult to guess. Likewise here, you stare at it for a while, you see that this is linearly dependent. You stare at this for a while, you know that this is linearly independent. Okay. Okay. So this is easy to see, and here is an interesting result, okay, which is I will leave as an exercise. It's not very difficult to prove. So two vectors are linearly dependent if and only if one is a multiple of the other. Okay. So this is an interesting thing to remember. One vector has to be a multiple of the other for the two vectors to be linearly dependent, otherwise they are linearly independent. Okay. So in fact, think about other trivial cases. Suppose I give you two vectors and one of them is the 0 vector, okay, then they are trivially linearly dependent again. Okay. So the 0 vector makes everything trivial in linear dependence, but assuming non-zero, all these kind of cases are interesting. They have to be multiples of each other. Okay. So something to remember. So let me this question to also remember. So supposing you think of R2, in R2, okay, supposing I have a vector here and a vector here, right, these two are linearly independent. Okay. Why? Because one is not a multiple of the other. If one were a multiple of the other, what should happen? They should lie on the line through the origin. Okay. So here is an example of linearly dependent vectors. So if I have a vector here and a vector here, these are linearly dependent. Okay. Why is that? Why is that? Because there is this line through the origin which connects both of them. Okay. So that's the idea. So one becomes a multiple of the other. All right. So keep that in mind. So in R2, linear dependence can be very easily visualized. Okay. If they lie on a line through the origin, then they are linearly dependent, otherwise they are not. So in general, in n-dimensional space also, if you can visualize, if you can draw a line through the origin, linearly dependent vectors, if there are only two of them, then they have to lie on that same line. Okay, so that's how it goes. All right, so two vectors, quite easy to think of linear dependence. Let's go to the next non-trivial case, which is three vectors, right? So from 2 proceed to 3. Okay, so let's go to R2 and then ask this question. Okay, so the first example, look at the first example, 1 0 0 1 and 3 17. Okay, are these linearly dependent? Okay, so you think about them for a while. It's not very easy, difficult to see that 3 times V1 plus 17 times V2 equals V3. Okay, so these are linearly dependent. Okay, what about the next example? 1 2 2 5 3 17. So in this case, it's not so obvious, right? I mean, how do you find a linear combination for 317 from 1 2 and 2 5? You have to write down some things and think about it for a while, but it turns out they are linearly dependent. Okay, so in fact, look at this exercise. Any three vectors in R2 are linearly dependent. Okay, seems like an interesting result. I am leaving it out as an exercise for you. Think about it. See how you can imagine, look at different situations and prove it. Any three vectors in R2 will be linearly dependent. Okay, so we will prove it in a different way later on in our class, but for now, try and prove it for the R2 case. It's an interesting exercise if you can show that. Okay, let's go to R3, the next more interesting case, and ask the same question. So V1, V2, V3, ABC. Suppose I give you an ABC vector. Okay, notice here what will happen if you look at V1, V2, right? So I can do A times, I have to do A times V1, if at all I have to match V3 as a linear combination, right? And then I have to do B times V2, okay? And if this has to be equal to C3, V3, this is if and only if, okay? I will write IFF, IFF means if and only if both ways, C equals 0, right? So this variable C is crucial to the story here. If in V3, the third variable is 0, third coordinate, so to speak, is 0, then V3 becomes a linear combination of V1 and V2. So they are linearly dependent. Okay, so they are dependent if C is 0. If C is not equal to 0, then they are linearly independent. Okay, there's no way you can make a linear combination of V1 and V2 to get V3 when C is not 0. If C is not 0, notice the third coordinate in any linear combination of V1 and V2 will always be 0. Okay, it's like you're stuck in the xy plane, you don't have any z direction, right? So only xy plane, whatever combination you do, you can never go there. Okay, that's the idea. Look at the next example here. Okay, so what do you do here? It seems much more tricky, right? 1, 2, 5, 3, 6, 7, A, B, C. Can you make a linear combination? Who knows, right? So you have to write it down and think about it. Later on, we'll see some general methods for how to approach these problems, how to do them very easily. For now, I will let you think about it if you can come up with some clever ideas for how to find such answers. Are these linearly independent or dependent? I'm leaving it once again as an exercise for you. Okay, think about it. So in general, we saw quite a few examples in the previous two slides for simple cases, small cases, how to establish linear dependence, independence. It seemed like you have to do some work, you have to think about it a little bit. Now push yourself to this large data regime, right, where you have 1,000 length vectors, hundreds of them given to you. If somebody asks you, are these linearly independent, how would you go about doing it? Okay, so we want a very efficient, simple solution. It turns out there is solutions based on ideas called Gaussian elimination. Okay. But before that, let me just give you a special case. So here's a special case, right? If each of these 100 vectors Vi, it was 1 in the ith position, okay, Vi has 1 in the ith position and 0 elsewhere, okay, in the first 100. After 100, I don't care, okay. So there's 1,000 length vector, the ith vector, say the 50th vector has 1 in the 50th position, 0 from 1 to 49 and 51 to 100, and then after that I don't care. Supposing you had 100 vectors like that, then it's clearly easy to see that they have to be linearly independent. Why? So if you make a linear combination and you have to get 0, right, each one of those coefficients has to be 0, right, otherwise you will not get this. It's easy to see in that case. Okay? So special cases like that for Vi are easy to solve. But what about the general case? It turns out you can use this notion of Gaussian elimination to reduce any general case to look like the special case. Okay? So that was the nice idea. You can manipulate the vectors to make it look like this special case. Okay, so we will see this later on in some other context. I'll give you some simple introduction to Gaussian elimination in another lecture. Okay, so it's possible to establish linear dependence and independence in a systematic, methodical manner. As of now, I'm leaving that as a puzzle to you. You can think about it, and then when we look at Gaussian elimination, you will see how the special case that I'm talking about here is all that is important. Okay. So the final piece here is once again a quiz for you. Okay, I'll urge you to answer these questions. There are some points, etc. They are not for actual grading. So please go ahead and submit these things. These exact slides will be shared with you. You can take a look at this quiz, answer them. It will give me feedback on how well you've done. Try to do it on your own. It will improve your learning and other skills. Okay. Thank you very much. This is the end of this lecture. We'll meet again in the next lecture.